indeterminate forms and Lhopitals rule. So we're going to learn a rule named after Guillaume Francois Antoine de L'Hopital, who lived from 1661 to 1704. Here he is, all dressed up, curly wig and nice clothes here. This was actually named after L'Hopital because he was the first to publish it in his calculus book, but it was actually first discovered by the Swiss mathematician John Bernoulli. And it's a rule to help us find limits when we have what we call indeterminate form. Let's look at these limits. It's been a little while since we've thought about limits. If we tried to find the limit as x approaches 1 of this first quotient, we see that when we substitute in a 1, if we tried to directly evaluate, that we would be dividing by 0. But one of the things we learned was we could do some algebraic manipulation, in this case factoring, and then we could reduce, and then we could directly evaluate, and we would get 1 over 2. The second one, if we tried to directly evaluate, we'd get the sign of 0, 0 over 0. We'd be dividing by 0, so that didn't work. We used a geometric argument and we discovered that this limit was 1. Looking at this third one, if we let x approach infinity, well, the numerator, that's as we go towards infinity, the natural log is going towards infinity. Looking at the denominator, we would have infinity minus 1, which is still infinity. So what does infinity over infinity mean? We'll return to this a little bit later. Looking at this fourth one, we would also get infinity over infinity, but one of the things that we learned is we could multiply numerator and denominator by the highest powered x that appeared here, and when we do that, we would have the limit as x approaches infinity of 1 over x, kind of squishing this in, plus 1 over x squared minus 2. Then as we let x go to infinity, this would go to 0 and this term would go to 0, and so we would be left with negative 1/2. So we did have ways of getting at 3 of the 4. We still have this fourth one. It turns out Lhopitals rule would enable us to find all of these limits in the same way. Let's consider the one that we didn't know how to find. It's like there is a battle going on between the natural log of x and 1 over x minus 1, because they're both going to infinity, but which one's going to dominate? Which one is going to win out in this battle? If the numerator wins, then the limit will be infinity because we would have infinity here. But if the denominator wins, well, if the denominator goes to infinity, then the fraction goes to 0. But there could be some kind of an in-between, and the answer could be some finite positive number. We're going to see how to determine who wins when we learn Lhopitals rule. First, let's talk about what it means to have an indeterminate form. The first two examples we looked at were of the indeterminate form 0 over 0, because when we tried directly evaluating them, we got 0 in the numerator and we got 0 in the denominator. The second two examples were the indeterminate form infinity over infinity. Now we're ready to look at Lhopitals rule. Notice the spelling here. It is spelled differently in various places. It's still pronounced L'Hopital, not hospital. Suppose f and g are differentiable and the derivative of g is not 0 on an open interval I that contains a except possibly at a. Then suppose that the limit as x approaches a of f of x equals 0 and the limit as x approaches a of g of x equals 0. We're going to be taking the limit of the quotient, so basically we're saying you get that indeterminate form 0 over 0, or that the limit as x approaches a of f of x equals plus or minus infinity, and the limit as x approaches a of g of x equals plus or minus infinity. Again, if we took the quotient, we would have an indeterminate form, this time infinity over infinity. So that's going to be one of our conditions for L'Hopital's rule, is that we have the indeterminate form, as well as we have the differentiable functions and the derivative of the denominator does not equal 0, except possibly at a. And then this is the conclusion that we could make with L'Hopital's rule. The limit as x approaches a of this quotient f of x over g of x equals the limit as x approaches a of the derivative of x divided by the derivative of g if the limit on the right hand side exists or is plus or minus infinity. All right, let's just look at that for a minute. So if we meet our conditions, our differentiable function and so forth, and our indeterminate form, then we can take the derivative of the numerator and the derivative of the denominator and then try and directly evaluate the limit. I'm going to look at a proof of this in the special case, and the general proof is much more involved. So our special case is f of a equals g of a equals 0. We have f prime and g prime are continuous, and the derivative of g at a is not 0. And it'll be easy to see then why the rule would be true here. And we're actually going to start with the right-hand side of the rule and come up with the left-hand side. So starting with the right-hand side, we have the limit as x approaches a of f prime of x over g prime of x. Because we have f prime and g prime are continuous and g prime at a is not 0, we can directly evaluate. So that equals f prime of a over g prime of a. Now let's go to the limit definition of derivative. So f prime of a is the limit as x approaches a of f of x minus f of a over x minus a. And similarly, g prime of a, using the limit definition, is the limit as x approaches a of g of x minus g of a over x minus a. Now we're going to use limit laws. We often have it in the other direction. We have the limit of a quotient equals the quotient of the limits. Well, we've got the quotient of the limits here, so we can say it equals the limit of the quotient. We can combine them under this one limit. Now if we multiplied numerator and denominator by x minus a, these would cancel. And then we take our condition that f of a equals g of a equals 0, and these two terms would be gone. And we would indeed have the limit as x approaches a of f of x over g of x equals the limit as x approaches a of their derivatives, and that was provided we had that indeterminate form and in this special case. Let's see how we use the rule. Here were our four limits, and we first verified that they are indeterminate. We saw that this one was indeterminate 0 over 0. So we're going to apply Lhopitals rule, and just some notation. You don't have to do this, but it's common to put little h over the equal. That lets us know that the reason these are equivalent is because we use Lhopitals rule. So Lhopitals rule says the derivative of the numerator, which is 2x minus 1, divided by the derivative of the denominator, which is 2x. If we take the same limit, it will be equivalent. Now we can directly evaluate, and we would have 2 minus 1 is 1 over 2 times 1 is 2. And that's what we got when we did the algebraic manipulation. So this was another way to get there using Lhopitals rule. The second one we saw was indeterminate 0 over 0. So Lhopitals rule says the limit as x approaches 0 of the derivative of the numerator, which is cosine x, over the derivative of the denominator, which is 1, is equivalent. Now we can directly evaluate. Cosine of 0 is 1, and that is what we had seen geometrically. We now can also get there using Lhopitals rule. Third one is the one we didn't know. This is that indeterminate infinity over infinity. So now we're going to see who wins. We have the limit as x approaches infinity. The derivative of the natural log of x is 1 over x. The derivative of x minus 1 is 1. Now if we let x approach infinity, we have 1 over infinity, and we know in the denominator becoming large, the fraction becomes small, and in the limit it goes to 0. So which one won our little duel? 1 over x minus 1 won the duel, because this went to 0, not to infinity, and not to some compromise. Looking at the one we saw that we were able to algebraically manipulate before, we're now going to apply Lhopitals rule, and we have the limit as x approaches infinity of the derivative of the numerator, which is 1 plus 2x, the derivative of the denominator, negative 4x. Now if we try to directly evaluate, we still get infinity over infinity. I didn't write that before, but we should have checked. We'd already talked about that this was indeterminate. Well, it's still indeterminate. It's still infinity over infinity. Well, if it's indeterminate, then Lhopitals rule will apply, so we could apply the rule again. We could actually apply it as many times as we needed to, as long as we'd get an indeterminate form in the next step. So the derivative of the numerator is 2. The derivative of the denominator is negative 4. And we have the limit like we had gotten before a different way. Let's look at this example then. And we have the limit as x approaches 0, and we have 1 minus 1 is 0 over 0 plus 0, which is 0. So we've got the indeterminate form 0 over 0. So we could take the limit as x approaches 0 of the derivative of the numerator, which is the derivative of negative cosine x is negative negative sine x, so sine x over derivative of the denominator 1 plus 2x. We applied Lhopitals rule one more time. The derivative of sine x is cosine x, and the derivative of 1 plus 2x is 2. Okay, easy to directly evaluate that. Cosine of 0 is 1 over 2. This is the wrong answer. So I want you to look at that for a minute and see why. I'm just telling you it is, but let's see if you can look at what I did and figure out what I did wrong. What I did wrong was I incorrectly used Lhopitals rule because this is not indeterminate. This is a common mistake. You get so happy to apply this rule because it makes things so simple. Just tend to sometimes apply it when it doesn't apply. You can see right here that sine of 0 is 0. The denominator is not 0. This is not an indeterminate form. So this is the point where we would directly evaluate, and we would get 0 over 1, which of course is 0. And looking at the graph, you can see as we approach 0 that we do get 0, and we would get an incorrect conclusion if we applied Lhopitals rule, because you cannot apply Lhopitals rule if you don't have those indeterminate forms. So just a caution.